All right. Good afternoon. Good morning, everybody. We are here for Flavio Del Santo's KISS seminar. This is, I've heard the beginning of this work or initial ideas of this work when I just started my PhD. So I'm very interested in hearing what the developments have been, or just hearing this direction explored more. And without further ado, Flavio, you have the stage.
Thank you very much, Andrea. Thanks for the invitation, and thanks to KISS for giving me this opportunity, and all of you who showed up, despite the beautiful summer weather outside. I suspect that everywhere else is kind of good. Anyways, I'm going to present today, exactly as Andrea said, something that is going to be kind of an overview and a bit more focused on the recent aspect of a full research program that have been carrying out with Nicolas Gisin at the University of Geneva, where I'm currently working. A research program that aims at exploring indeterminism mostly, and the contrast between determinism and indeterministic descriptions of nature, of course, in quantum mechanics. So the hope, all this work is conducted, of course, in the framework of quantum mechanics, with the aim and scope of quantum mechanics, but at the same time, instead of starting from the quantum formalism itself, we wanted to try to understand how much can we investigate the problem of indeterminism within classical physics, and from that, trying to approach the quantum. So this, I hope it will become clearer during the talk. So let me start from the first part, really the general idea of this research program. Let me define what I mean by determinism. Determinism is a formal feature of a theory, and if you want to have like a theory of so if your philosophy is telling you that the theory is somehow reflecting what's out there, you might want to also infer what is actually whether there are events and dynamical processes that are either deterministic or indeterministic at the fundamental level. But let's start from the theoretical level, and to explain what is determinism, we should start from the classical theory. Let's say for classical mechanics or classical electrodynamics. So let's start from classical theory. We know that I think you see my pointer, my arrow here. Yeah, thanks. Okay, so when we say that classical physics is a fully deterministic theory, what we mean is the conjunction of two different assumptions. One is the fact that dynamical laws, if we're talking about the classical mechanics, those are Newton laws or any equivalent Lagrange or Hamiltonian formalism. Anyways, they are they're usually in the form of ordinary differential equations, and by their very structure, they connect. They have like there is theorems of unicity of the solutions, such that if I plug in the sufficient boundary conditions or initial conditions into the equations, there exists a unique continuation in the parameter time, both in the past or in the future, which is unique, right? So if I plug in, but this assumption, I have to spell out more the assumption. What does it mean that I have suitable initial conditions? It means that I'm selecting at a certain time t, so I slice the time, I select the time t, and I say that there exists the state of the system. What I call the state of the system is an n-tuple of real number, infinitely precise. So the state of a system, if you describe this in phase space, is nothing but a dimensionless mathematical point. Only with this pre-assumption, together with the form of the dynamical laws, I can claim that classical physics is deterministic. So I need a certain shape of a state and a certain shape of dynamical equations. These two together lead to through mathematical theorems. These together lead to the uniqueness of trajectories and their continuation from time minus infinity to plus infinity, and this is what I call determinism. Give me one state of this kind, give me the equations, I can tell you the corresponding state at any other arbitrary time. Good. So this has been for many years, for centuries, has believed to be the case, that these equations were actually, this theoretical structure of states and dynamical equations were actually perfectly describing what is out there. And there is the famous description of Laplace, that having enough computational power should exist. So if there were a demon out there that has at the same an infinite intelligence, he says, that would know with perfectly all the positions and momenta of all the particles in the universe, these would, for him, nothing would be past or present. Everything would be past or future. Everything would be present to his eyes. So you can have this big picture, this kind of frozen picture where time becomes like just a coordinate to connect different states, but there is no actually, not even causal connections. It's just like prescriptive connections. Okay. Just to give a small historic, since I'm very interested in history of physics, let me give a small historical curiosity, if nothing else, is that the first one to question the possibility of having determinism at the fundamental level is not, as many would think, the advent of quantum mechanics, but there have been already in the decades before the formalization of quantum mechanics a few doubts about the possibility of having perfect determinism. And this is the school of statistical mechanics, that there are those who introduced actually probability in the natural sciences. Before that, probability was just something that was heuristically developed within game theories, like theories really of bets and games of chance. But it is really with Boltzmann and Gibbs and the kinetic theory of gases and statistical mechanics that probability enters the scene of natural sciences. And of course, with a story that we keep telling to each other as physicists in the textbook is that this is just a mere epistemic notion of probability, where we cannot have enough computational power in the sense of Laplace, and we have to discretize the phase space and only give like partial knowledge of what we know, and that's how we introduce probabilities. But actually, some of these people started thinking that perhaps the fact that we have these probabilistic behaviors is that there is nothing else below these limits. So, for instance, Boltzmann starts thinking that the fundamental equations of motion of individual molecules maybe will turn out to be only approximate formulas which give average values. So he questions the individual character of deterministic laws. And the person who most systematically develops this idea of classical indeterminism is another Viennese physicist who has been a bit forgotten perhaps today, but was very influential at that time, Frank Serafin Exner, who really thought that everything that happens in nature is the result of random events. So at the microscopic level, before and independent of quantum mechanics, he believed that everything was a result of individual events. And maybe this could be surprising, but Schrödinger was a pupil of Exner, and many think that Schrödinger was a committed determinist. This is also a wrong narrative, in the same way that people think that Einstein and Bohm were committed determinists. They were also very open-minded, and they believed that there can be actual chance and randomness at the bottom of nature. And then this is a quote from Schrödinger that says, "As a pupil of the venerable Franz Exner, I have been in intimate terms for a long time with the idea that probability, not macroscopic lawfulness, but perhaps absolute accident, forms the foundation of our statistics." Anyways, this was just a parenthesis. Let's go back to the mainstream story. That is what interests us the most now. So what we usually say is that with the advent of quantum mechanics, that determinism really becomes a concept at stake. And how is quantum mechanics possibly undermining determinism is through Heisenberg uncertainty principle that tell us that if you keep the same picture of phase space I showed before in classical physics, here in quantum mechanics, this reduces the minimal volume. So this imposes a bound on the minimal volume that the state can occupy in phase space. So it prevents, by the very nature of the very structure of the theory, by the commutation algebra, that the non-commutative algebra that characterized quantum theory, that you cannot have these single points in quantum theory. So these mathematical points as a state, but you have like this finite volume, which is quantified, which is lower bounded by h. So for each degree of freedom, you have a Planck constant which characterizes the minimal amount of volume in this way. And moreover, Bell's theorem tells us that under certain assumptions, so if you want to maintain locality and independence of the inputs, then quantum indeterminacy cannot be explained away by incompleteness. You cannot have additional hidden variables that can actually lie within this volume and complement the theory if you want to maintain other standards of your physical theories. So these two are good hints, if not like comprehensive proofs that nature is perhaps indeterministic. All right. However, if you are to abandon certain of these assumptions, that for instance locality, you can actually build a deterministic interpretation of quantum theory. So if you look at this table on the right hand side, you have like the standard quantum theory with a measurement postulate, that you have like this update of the states, which is exclusively probabilistic, and you have this uncertainty in the state that cannot be reduced to a mathematical point in phase space. But then there is de Broglie-Bohm or Bohmian mechanics, where you have like additional hidden variables, that is the initial positions of particles, or the whole state of the universe in many words. And these have like a deterministic interpretation. These provide deterministic interpretation of the quantum formalism. You have to pay either other prices, but you can do that. Whereas it seems that Newton's classical mechanics, with the initial conditions taking values in n tuples of reals plus Newton's equations, as I showed at the beginning, was a monolithic, well understood foundations of the theory, and there was no possibility of other interpretation. So this is kind of the motivation for, at least for me, for our work with Nicolas Gisin, has been like, can there be some consistent interpretation of classical physics which recovers indeterminism? So instead of completing the theory, can we incomplete the theory in a consistent and meaningful way, such that you can draw this parallelism with quantum and classical? And the idea is that maybe we can learn something about general theoretical frameworks that is not specific to quantum theory, that has a lot of, this quantum mystery that we fill our mouths with, perhaps is more of a historical accident that has developed in such a strong sense. And maybe you have like more general interpretations, classes of interpretations that share the same features or problems of quantum physics. Good. So let me just spend a few words of how we have approached this. Is definitely not the only approach you can have to find an indeterministic interpretation of classical physics, but this was for us also physically motivated. So the fact that we have this n-tuple of real numbers as an assumption on the state of classical physics seemed to us a very strong tacit assumption that goes into the textbook of classical mechanics. What we have called the principle of infinite precision, it seems that textbooks manuals of classical physics tell you that there exists at any instant in time an actual value of every physical quantity with infinite predetermined digits. So you have you have to have the whole infinite information about where a particle is and how fast it goes to actually claim that there is determinism, right? So if we actually relax this principle of infinite precision and you substitute it with the principle of finiteness of information density, so a finite volume of space can only contain a finite amount of information, quantified by any sensible measure, like Shannon entropy, or you can have like Kolmogorov complexity of finite Kolmogorov complexity. So you can substitute the real numbers only with the computable ones, for instance, and this gives you a fulfilling of this principle of information density. Now, in this case, initial conditions are not anymore the full real numbers or n-tuple of real numbers. So you cannot have them if you renounce infinite precision. And this, together with existence of chaotic system, make it possible to have this uncertainty spread as much as you want. So if you have like that your initial volume in phase space is finite, this can be stretched also in a fractal way, but it can be like really stretched and squeezed as much as you want through certain dynamical systems, in particular chaotic ones, in which any epsilon of initial uncertainty, indeterminacy, really, like ontic indeterminacy, can be is enlarged exponentially as time passes. And in the words of Nicolas Gisin, in one of the early works about this, he says that basically we can regard the real numbers, the full real numbers, as the hidden variable completion in a very similar sense that Bohmian mechanics does in quantum mechanics. So if you take like this finite information version of classical mechanics, you can complete it by adding filling the holes in the real line with all the real numbers. And so one can add supplementary variables to the alternative classical mechanics in order to restore determinism. It suffices to add the mathematical real numbers. So we have like, I will show later how it goes, this finite information interpretation of more in detail. But anyway, just that you give like an intuition about this. So you have again the standard story, what I call the orthodox interpretation of classical physics, with this mathematical point here. Whereas we have substituted the mathematical point with any finite region and shown that this leads to indeterminism. Now, as you see, this is already evening out the difference between classical and quantum physics, in the sense that these two figures appear very similar, with the only difference that we don't have in our finite precision indeterminism a new constant of nature that quantifies this minimal volume. We only impose it as finite. So you can recover classical mechanics from this finite precision indeterminism with no revolutionary move, but just setting one parameter to say how big is this volume, instead of saying that is between between 0 and any finite number, but not infinite. Good. So indeterminacy in the initial condition is how you get indeterminism of the future and possibly of the past. I would tell a few words about this. Let me stress one thing before we go further. What I want to tell you is that notice that this is really an interpretation in the same sense as quantum mechanical interpretations are, because we do not change the equations of motion. We only change the interpretation of what a state is. So in the same sense of quantum mechanical interpretations, is not like in the GRW spontaneous collapse interpretations where you actually modify the dynamics. Here there is no stochastic dynamics. All the equations of motions remain the same of the orthodox and of the standard classical mechanics, but we go acting at the level of states. What is a state in classical physics? And this is very similar to what is the debate based on the quantum interpretations. All right. So let me talk now more about a more recent work we have in this overall program, which we have called potentiality realism. So we wanted to really find a general, like this, a more of a philosophical stance about physical theories. And we want to find, like, we had a series of desiderata that we wanted to pursue, and maybe we can discuss later why this can be useful desiderata. But we want to give an interpretation that can be used in any theoretical framework, maintaining and realism and indeterminism, which are very much confused in the philosophical and especially physical literature. Some people also with discussions about Bell's inequalities, often people try to confuse what realism and determinism is, and they say, this is called local realism because they cannot be, the variables cannot be predetermined before the measurement. This doesn't mean necessarily that you are that you're not upholding realism, but mostly that they are not deterministic. On top of that, you can either be realistic or not. So these are two logically distinguished concepts. And this somehow is a way of seeing things, the one that I'm going to present now. So forget for a moment everything I've told you. Like up until now, I've only given you the motivations and the general trend. What I'm telling you now, it's really like, forget the specific form of theories that we're talking about. I'm not talking classical, quantum, or even possibly, you know, GPT, post-quantum, box word, or whatever. So it's really like any theoretical framework that can either be realistic or not, deterministic or not, and I'm going to just give you a story of how you can regard these things. So in an indeterministic world, one should be able to produce non-necessary events. This is like non-necessarily events are a necessary condition for an indeterministic theory. So new information that was not present in the world is somehow created as time passes. So that you have a concept of becoming. There is something that even having a full, so remember the Laplacian story. So Laplace is telling you, having a complete knowledge of what's going on, you're able to predict with, so you're able, the universe is able to predict. The universe knows what the next step is going to be. In an indeterministic world, you want to have at least one bit of information that was not computable, having also access, even having access to the whole thing. So you have like some variable, for instance, a bit, j, that at a certain time is not determined, and it becomes determined. So you have the concept of becoming. You see, this sophisticated animation shows what's the process I have in mind. Poof, from indeterminate to redetermined. There is a becoming. Now, often, actually for very, very long, this has been thought to be something that must happen completely randomly. So for very long, people have thought that you have to abandon the concept of any concept of causality. You cannot, like, there is an event that pops out, and there is no way that you can connect it to anything else that happened before. If it was not predetermined by the thing that were there before, it means that there is like a toss of a die, and then you have like a 1/n probability that this thing is happening and nothing is different. However, since the late 1950s, mostly in the philosophical literature, and then physicists and other scientists slowly tried to follow this trend. Well, actually something that was already discussed by Aristotle, but let's say more in the scientific literature, modern scientific literature, was like formalized more in the 1950s, is the concept of potentialities. So instead of having like a completely fully random toss of a die, you can think that events that are indeterminate actually happen without the possibility of knowing which of the possible outcome is showing up in a certain run, but what is fully determined is its potentiality. So you can associate a measure of likelihood that is an objectively existing property of the system and all his past causal history. And this causes the potentiality of something to be coming. Okay, so there is an extra structure to the, so you have at the same time, okay, let me go through the next slides and it will become clearer what you have. So let me restart from here. So let's go to the definition of what is a physical state. So a physical state, especially in a realistic theory, defined in the philosophical, in the philosophy of science, for instance, here in this entry by Jeremy Butterfield, he says that the physical state is a system's maximal or complete set of intrinsic or possessed properties. Now, in the standard physics, this means that outcomes are manifestation of actually pre-existing determined properties that get unveiled, right? So you have like what is a state is the collection of its properties, its length, its position with respect to a certain reference frame and whatever. Like you have like you put curlies and in it you list everything that exists about the object is a collection of numbers that you can relate to different properties, numbers or descriptions, it doesn't matter. So states in the standard physics are collections of actual values, usually mathematically associated with n tuple of real numbers, that are assumed to exist, well determined. So is a collection of possessed properties. And in this new interpretation that I'm proposing here, potentiality realism, also here systems are a collection of possessed properties, but the properties are potential ones. So let me clarify. Outcomes of measurements are actually dynamically realized. So they come into existence, creating new information from a set of mutually exclusive potential outcomes. So what exists before the realization at any given time, the element of reality, the state of a system, the collection, the maximal or complete set of intrinsic or possessed properties is the collection of its potentialities to realize any of the possible outcomes. So you just substitute what is the maximal piece of information, but you still have philosophically the same concept of properties. Instead, they are not existing forever, since ever, forever as frozen properties of the system without dynamical realizations, but it's just the potentiality of happening. And okay, so these potentialities that you can think really of tendencies, like as a kind of a force that has a certain is a causal force of variable strength that tells you like how much like is that one event can happen or another one. Have the following properties. They carry the causal structure. Tickling, so moving something about the object, changing something about the object doesn't influence necessarily immediately the position of the object, for instance, but it might influence the tendency that the object behaves in a certain way in the following period that you can define in the following measurement, for instance. So it has a definitely causal structure. What you do influences, it has a kickback. It influences how the behavior of systems. It just doesn't do it as a one-to-one connection as a necessity, but it just does influence the state of the system in terms of collection of potentialities. It is objective in the sense that it is not related to one particular observer doing this. There is nothing like consciously intervention in this. It can just be like evolution of propensities as an objective set of properties of the system. And again, is not governed by necessity, so it entails determinism. And these potentialities with this structure have been encapsulated usually in the literature with different variation in the concept of propensities. So propensities were introduced at the beginning by Karl Popper in 1957, but as an interpretation of probabilities. So he was saying that probabilities are physical. We will see later how this is problematic and we propose something different. So don't bind the propensity, don't think of the propensity necessarily as actually formal probabilities. Think of them more as an element of reality which connects causally event A to event. So actually, let's read here. So let's call P this propensity. You can give the same kind of notation than a probability to make things worse. But I don't think of it exactly as a probability. I will in a moment define what's the difference between a propensity and a probability. But this propensity P of an event A to happen, given its causal condition, is the actual tendency, is an objective causal property that not necessarily entails that if the causal condition obtain, then A obtains. It tells you that given these causal conditions, there is a certain likelihood, which is a bounded strength between a minimal and a maximum, say 0 and 1. It gives you the likelihood of A to happen if this causal set of causal connections obtain. And there is nothing more to know rather than this, right? So that's important. It's not that if I had like the complete set of causal connections, I would be able to get rid of this P and A either happens or not with certainty. The causal connections are a complete set. There is nothing else in the universe that can causally influence. It can be like the whole past light cone, if you want to think relativistic, of the event A. Given the whole past light cone, there is a certain propensity for A to happen, which is a number. And these propensities also allow you to think of events as actually developing in time. And by doing this, it indicates somehow the concept of present, in the sense if you can build a graph of everything that is all these nodes are like the possible events, and if they have a blue arrow, it means that they are causally connected. But these blue arrows are the propensities, so they are weighted arrows. You have like a certain likelihood weight that tells you whether it's happening or not. But as time passes, these propensities, so some events actually do happen, ruling out their alternatives. So imagine that A2A and A2B are mutually exclusive events, is either heads or tails. They cannot happen at the same time, but you have a certain propensity at time when you are at E1, you have a certain propensity that these are going to happen or not. But then as time evolves, this coin flips, and you realize that it ends up A, which let's say is tails, and so it cannot be any more heads. So there is a second layer on top of the whole causal structure. That is what actually happens, which is the red arrows. And then you have a manifold in this causal graph that is separating all the subgraph that has already obtained, of which the propensities are all zeros or ones, because they have already actualized either one or the other of the possible outcomes. And then you have the future, that is where the arrows are still all blue. So things have not yet actualized. There is a question, I think.
Yes. Hi.
Yeah, please, Wolfgang. Hi.
Hi there. Yeah, this is very interesting, but I really like this talk. But I have a bit of an uneasiness about the idea that, and since you're here talking about the present, future, and past, about the idea that events come into existence.
Yeah.
I mean, isn't there a tension with relativity? And couldn't you make sense of everything that you just said without ever drawing this line of a present? I mean, these red arrows, they just exist by themselves. You don't ever have to speak about something coming into existence, no?
Well, somehow, I mean, there is some tension with relativity. This is true. We have a paper later. I will mention what's so. if you want to maintain these in a relativistic setting, you need somehow to have the parametric time, which defines, the Minkowski space-time, or like the relativistic time, as a manifold, as one of the coordinates in which you embed the manifold. And on top of this, you need to have some kind of creative time, which is the one that tells you when you have like these discrete clicks that are making one event becoming determinate from indeterminate. It was believed by Rijek and Putnam, they had an argument that genuine indeterministic events cannot happen in a relativistic setting. I have a paper, now I don't think I will have time to show, but where we rebut this argument in the way that you need determinacy to also be a relativistic concept. So if an event gets determined, let's say E3A gets determined here, its determination travels within the speed of light. So for an observer that lies outside the light cone, it will never be determined with respect to this one. And if it's in the future light cone, only when the light rays reach another observer can this say that the event E3A have been determined. So somehow it's light cones of determinacy, is not anymore single events, if you want to embed this in a relativistic setting. I can give you the reference. I can give you the reference later.
Let's just yeah. Thanks for the detailed answer.
Yeah.
I see that also Claudio has hands raised, but for the interest of presentation, Claudio, go ahead, ask the question if it's like a short clarifying question, but we'll have plenty of time for discussing afterwards. So
I mean, it's more remark. I mean, what you're saying here is essentially exactly like 100% compatible with Fröhlich's events trees histories approach, and he has a relativistic formulation of it. So that's possible. That's done. I mean, yeah.
Yeah, agree. Thanks. Okay. So yeah, this about time anyways was just a remark that I find it a nice way of with these histories that evolve to define how you can separate what it has happened from what will happen in terms of this dynamical process of propensities. Okay. Now I told you already that propensities are not probabilities. Well, this is to be discussed. And how do I show you this? Is in the following way. So, well, this is called in the literature Humphrey's paradox. So Humphreys in the 1980s rebutted the idea of Popper that propensities are just an interpretation of probability. Popper was saying that we should interpret probability calculus neither as a subjective lack of knowledge nor as frequencies, but as a propensity, in the same sense that I more or less told you, like as a single shot property of an object and its surroundings and its environment. What I've told you is a more refined version in terms of like causal connections. But he thought that this P that I've written down before is formally a probability, so that there is a one-to-one correspondence between these more metaphysical idea of having this non-deterministic causal force that connects events, and that this is quantified by a probability at the formal level. Now Humphreys put out an argument against this, and I have reformulated it in my recent paper as a no-go theorem, basically. Very basic one, because it shows two assumptions: that either propensities are this kind of quantifying indeterministic causal connections between single events, not long sequences, long runs of repetitions. So they're not interpreted as frequencies, but really as an indeterministic causal connection between single shot events. And the second assumption, that propensities are probabilities, therefore they satisfy Kolmogorov axioms, and in particular Bayes' rule. Okay, so the assumption, the conjunction of these two assumptions is untenable. And the easiest way to see it, there is more sophisticated ones with multiple events, but there is a very simple way of seeing this, that is the following. If I define causality in this way, call an event C the cause, and call the event E its effect. So you want the event to be causally related in a cause-effect manner. So if I have the probability of the cause given the effect, these small p's are really probabilities, right? So I have the probability of the cause given the effect. You want it to be only the probability of the cause. You don't want that there is a backward causation from the effect to the cause. If you condition or not whether the effect will happen, you want the cause to have like an independency from its effect. However, you want the opposite to not hold. You want to have a non-trivial causation. So the actual definition of why calling an event C the cause is that if I take the probability of the event given its cause, it should not be independent of the cause. So you don't want, if you reverse this thing, you don't want to be only P of E given C. You want to have it different from P of E. However, you have Bayes' rule that allows you to write one in terms of that as a linear function of the other, right? So you can take the probability of the effect given the cause, reverse it in this way. So if you plug this causality condition into here, you will see that P of C goes here at the numerator. It simplifies, and therefore you just are left with P of E given C equal P of E. So you run in a contradiction that you wanted the cause to be non-trivial. Yes, Manuel, please.
Sorry, I don't understand the causality condition. This, I mean, condition that is an intervention on the effect, or I mean, P's probabilities, so the propensity. I don't understand the causality.
These are probabilities. These are probabilities. Like in any GPT, causality is defined exactly like this. Like you want to have like the probability of a certain event to happen given its effect must be independent of the effect. So it creates somehow a
but on the intervention,
a causal arrow that you have like an asymmetry in effect. You call the cause a cause and effect an effect because this holds and this does not.
Okay, so it's not a simple conditioning, it's an intervention on the effect to define the causal arrow. Because I mean the causality framework is compatible with the probability. It seems that causal
in the causal graph thing, yeah, it's they define it as an intervention. Yes, in the causality framework is defined as an intervention. I think that is a trivial condition for cause and effect. Yeah, I understand what you're saying. Yeah, sure. Okay, it's an intervention then. Yeah.
Thank you.
But yeah, sorry, can you clarify? Because like the probability that I'm like the fact if I'm wet, the probability that it rained is definitely higher than it didn't rain, right? So the probability of the cause given the fact that I'm wet is not independent of the fact that I'm wet.
Well, yes and no. They're not. So the probability you're not claiming that you're influencing. So you want to have this to be a causal connection, right? So the probability of today's very hot day here. The probability that I drink a glass of ice cold water, given that it's very hot outside, I definitely trace a causal connection with between these two things. But the fact that you drink an ice cold glass of water certainly does not influence, or not non-trivially, that is gonna raise the temperature outside. So clearly causality in this sense has an arrow that you cannot trivially reverse. Then of course probably okay. Then what you're telling me is that but I mean clearly in drinking, clearly these two things are correlated. So one thing is correlation. One thing is that you claim that this correlation is due to a causation, and probabilities. So what I claim is that probabilities are the perfect tool to describe these correlations, and they work perfectly because of this. You can reverse them because you find that every time I drink ice cold water is probably is very highly correlated with hot weather outside. But one thing is causing the other and not the other causing the first. So probability, since it has a base rule that is symmetrical, that makes symmetrical the argument that you can switch around cause and effect, definitely is good for correlations, but is not the right tool to describe what I want to tell you, that one thing is causal and the other is a construction in the other direction. Carlo, please.
I'm also not convinced by this argument, Flavio. That causality, that definition of causality that you use, it's not convincing, because that's not what we mean by causality. In fact, to say what we mean in causality is notoriously tricky. There's a lot of debate about what is causality. If you just take think in terms of frequency and give the probability of E and C, okay, that determines everything.
Mm-hmm.
Right? Imagine that many things have happened, and there is no reason for that causality thing would be true, even in situations in which we do say that that C is a cause of E. So I think that you're using causality in a way which is not well defined here, or if you're defining causality in that way, that's too strong. That's not what we mean by causality usually, it seems to me.
Okay, and I'm not sure I got the counter example to. So I understand what you're saying, that you think is too strong, but I'm not sure. I'm not sure why it's too strong, actually.
Is that a definition of causality for you?
Yeah. Yeah, that's the definition of causality, I guess. Yeah. So it's a definition of I don't know if it's the definition of causality. It's a definition of a given. Yeah, it's a definition of a cause and an effect. Is a relational property of two events, and is the definition of calling C a cause and E an effect if this holds and this has a different here. So there is this asymmetry between one event is influencing the other if conditioned on, and the other event is not conditioning. So event C conditioned on E is independent of E, and condition of E given C is dependent on C. This is my definition of what is a cause and what is an effect. And I think it's so I don't know if it's really generally calling definition of causality, but if causality is defining what is a cause and then if the relation of two events called cause and effect, if this is causality, then it's definition of causality. That's what I'm saying.
Okay, this is going to be longer, so I suppose we should pick it up.
Yeah, thanks, Karen. Was there another hand, some clarification? No. Okay.
I was just thinking maybe the confusion comes from the idea of probability, because when you say the probability of the cause given the effect, it's basically using the terminology probability, not in terms of, given the example, for example, of Andrea, that now I'm waiting because it was raining. The information that we usually associate to the probability that I'm wet, given that it was raining, as an implicit error of time. So we are talking about two different concepts in terms of probability. One is a probability in terms of how much information can I get about the past that it was raining, given that I'm wet, even if the fact that it was raining is an event that was not caused by the fact that I'm wet. So there is causal independence in this sense because there is an explicit actually arrow of time. But the concept of probability that I'm wet, given that it was raining, it's something that we are asking about the past in terms of a possible information on an event. That it's something that might be different from this causal relations. And one description is just a matter of how much information can I have of what was happening in the past, given some that I measure in the present.
Yeah, I agree. I mean, I think how much information we have, I think, is what I meant by like the correlation that you can like. A correlation is a concept that is definitely symmetric, right? It's a compound condition on two events. And then you can say every time this happened, the other happened, every time the other happened, this happened, and you can correlate them. And here instead you want to draw like directional arrows in terms of like I call them causality. Maybe you need to, yeah. I think you're right in this. Ale, yeah. Okay. Should I go on? Good. Yeah. Anyways, this is okay. This is not my argument. This is a Humphrey's paradox. Okay, I think it's correct actually, but yeah, what I want to say, however, like if you buy the argument, this is my work instead. I should say that so one way to it's in this form of an or-go theorem is the conjunction of the two assumptions that cannot hold together. So one thing that you can renounce is just saying, okay, forget propensities in the way you want to have. They cannot relate in individual events. Maybe they're just like propensities are basically frequencies, like they are like influencing a whole infinite, possibly infinite repetition of things, and they're not the relating causes to effect directly. So they're not the thing I have in mind. But if you want to continue with to push further the idea I have in mind of being like this causal, non-necessary causal relations, then you have to abandon Bayes' rule. You need to find like a different axiomatization of these objects mathematically that doesn't have a Bayes' rule. You cannot reverse in this trivial sense P of E given C as a function of P of C given A. However, they can also not be fully arbitrarily different from probabilities. This is what I want to say, that since so both of them, propensities and probabilities, so if we settle the case that propensities are a measure of the causal structure and probabilities are a measure of the correlations among events, they both have to comply with some form of observed facts. And the way that we relate the observed facts is through repetitions and the law of large numbers. So also propensities ought to have a law of large numbers, because if you want to say that there is this non-necessary causal connection between two events, if I am able to prepare IID, identically prepared identical and distributed events in and do many repetitions thereof, I should be able to get information about the propensity itself. So the way that you measure a propensity is actually to do many repetitions and see how many times one thing happened. If you're able to reproduce the same causal structure, the same causal assumptions of the event that you call the cause. So if you have the same preparation, exactly the same preparation of an event, you can repeat many times and see how much this propensity, even if it's unique for the single event, you can have that an event is characterized by the same propensity, and measuring many times, you can get access to this propensity. Approximate access in the same way, and probabilities are built exactly for this purpose. They're built to approach the many repetitions. Therefore, both of them are related to the law of large numbers. So both of them should approach better and better the frequencies of different for even if like conceptually they're different objects, clearly they have to approach these frequencies if they want to describe on the one hand propensities, the causal relations, and probabilities, the correlations. So both of them have to be related by this. Both of them have to encompass certainty and impossibility. A fundamental one in case of propensities, a probabilistic one in terms of probabilities. Like probability 0 doesn't mean that the thing is ruled out by necessity, but it means that you have like well, you know how it works in set theory. You can have like measure 0 subset. So probability 0 that are not impossible things to happen, but they're like it's a measure. It's a measure theory, the probability theory. So anyways, certainty and impossibility with their own small differences. So they're all bounded between any two numbers, and you usually normalize them between 0 and 1. And then if you want to apply also these propensities in the same way that you think of irreducible probabilities in quantum theory, to comply with quantum mechanics, they ought to be non-local in certain sense. And this idea that propensities might not fully be probability, but being somehow similar to probabilities to many extents, like the empirical access you have to both propensity and probability is the same through Euler's law of large numbers, led some authors to call this a non-Kolmogorovian probability theory, with the analogy of non-Euclidean geometry, which is a geometry which is almost Euclidean because you have most of the axioms, but you have to drop one, the parallel one. Here you have to drop the axioms, the base rule, or the axioms that lead to the base rule if you want to derive it as a theory. So propensities as non-Kolmogorovian probabilities. Okay, how am I doing with time, Andrea? How much time do we still have? Sorry.
So it's been an hour, but we interrupted you a bit. But let's say
okay,
10 minutes,
let me give you 5 minutes, and yeah, last 5 minutes. Okay, so I don't want to go in detail in this slide, but I just want to tell you like a few applications we have used them in actual theories. So this is my like a glimpse of mine in something went wrong here with this slide, but my interpretation of classical indeterministic interpretation of classical physics using propensities. The idea is that physical variables don't take values in the real numbers, but into what we call fixed finite information quantities that are infinite order strings of propensities, such that their full informational content is finite. So they comply with what I was saying, the finite information constraint. But so each digit, so if you have like the length of a ruler, these can be any number between 0 and whatever x, but the x is not a real number, but it's a blurred number that has like all its digits, like q1, q2, and infinitely many digits, and each of them are associated with a propensity to become, let's say, if it's in binary expansion, 0 or 1. And then you can have, for instance, a cut after which everything is random, such that is a compressible number. Kolmogorov complexity is finite, so you have finite information within this number. But so you just change the idea that you don't have the full number given, but you just have this collection of propensities that tells you what are the numbers of your theory. And this is absolutely consistent and equivalent to standard classical physics, or at the observational level, especially because you never measure real numbers, you always measure rational ones, basically. And so this somehow is what I was telling at the beginning. If you substitute this fix by real numbers by fix, plus Newton's equations, you feel this gap here in determinism, classical indeterminism. Other application, very quickly, I have mentioned this already. Determinacy itself, indeterminacy, if you want itself, propagates in space at the maximal speed of light if you want to have this compatible with special relativity. And here you find the reference to my paper, The Relativity of Indeterminacy, where I discussed this. And another application is that in a fundamental indeterministic with finite information theory, it might be that, so I have a toy model that shows that also the past can get erased, and you have like indeterminacy in the future and also in the far past. So also this is a small advertisement. So the open past in an indeterministic physics is another paper using this idea of propensities and showing why can we have the open past, so that we have like some past gets removed as time passes, but why there is also, so that in the toy model there is a natural explanation of why we remember the past, but we know so little about, we can predict so little about the future. So the asymmetry between past and future comes about from information theoretic consideration in the with this model of propensities. And very last point I want to make, 30 seconds, is that this idea of potentiality versus actuality is for me the essence of the measurement problem, also the quantum measurement problem. So having these propensities tells you that you have somehow is not a coherent superposition. You cannot like interfere propensities like in quantum mechanics at the classical level, but you can think that propensities are nothing else but this collection of different possible outcomes that with certain weights, but as time evolves, only one of them will get actualized. And what caused this, when, how, under what circumstances a single outcome is realized out of its potentiality is also the quantum measurement problem. Why from a superposition at some point we observe a single outcome? I just want to tell you that any indeterministic interpretation of physics suffers from this kind of problem. This is a feature of indeterminism. It's not a feature of quantum mechanical formulas per se. And you have also the same interpretations in this potentiality realism that I've told you. You have different classes of interpretation. You have a Copenhagen interpretation, if you want, for instance, that propensities get determined when a higher level imposes it. So for instance, when you couple something that is very well determined, you have like a ruler that you know very precisely how many divisions it has. You couple it with another system, and perhaps there is a physical interaction that is forcing the other one to collapse to its actual, so the propensity from being very blurred becomes very well defined, very well determined. You can have an objective collapse theory where propensities actually have their own dynamics, and they spontaneously events collapse at a certain point, and you need like to modify to find the modification of the dynamics. You have the Bohmian interpretation, which is the standard, the orthodox interpretation of classical physics with real numbers. Is nothing but the Bohmian mechanics, where you add perfect initial conditions in quantum mechanics. And you can even have a many words interpretation of propensities if you reject the idea that you actually actualize. Things can like that, everything that can happen actually happens, and the word splits without incoherent histories, and this is perfectly fine at the classical level. You don't need to have like a linear Schrödinger equation with a quantum state to think of this kind of many possible outcomes. It's any deterministic potential theory has it. And so that's the conclusion slide. What I want to say, a bit provokingly, is that potentiality realism brings closer together quantum mechanics and classical physics, not by pushing classical physics, not by reducing the mystery of quantum mechanics, but rather increasing the mystery in classical mechanics, showing that different interpretations of any theoretical framework can lead to many problems that we have historically considered to have a quantum nature. Fundamental indeterminism is not uniquely quantum. The measurement problem is not uniquely quantum. plurality of interpretation to solve the latter problems are not uniquely quantum. What is uniquely quantum, seems to me, at the moment at least, is the fact of the algebraic structure of incompatible measurements, the fact that everywhere there is an H bar, a Planck constant appearing. This is really what qualifies as quantum, because both the size of the volume in phase space, how it's constrained, and violation of Bell's inequalities, which is where really H appears, there you cannot have a classical counterpart, or I didn't find any possible examples to find the incompatible variables and violation of locality using any indeterministic theory. Thank you very much.
Thank you, Flavio. Please let's join me in thanking Flavio for the talk. And so there was, obviously you started already 2 discussions during the thing, so this would be like a natural place to pick them up again.
Yep.
And otherwise, let's maybe start with raising hands, and then we see maybe we're moving to just full discussion mode. So Carlo raised his hand already.
Yep.
Yeah, I don't know. There's a part of this which I found very nice, very convincing. This pointing out one can rethink classical mechanics in ways which are much more similar to quantum. In fact, one has to some extent, by realizing that the full information and interpretation of classical mechanics is a sort of idealization, also a good one. But this story about propensity, I'm not sure I get it. So maybe it's my anti-metaphysical stance here. But let me be precise. Let me go back to the question that I was asking, and then said let's do it, because maybe it has to do with the general thing. So maybe I don't know what you mean by propensities, because and therefore I don't know what you mean by causality. And actually, before going to the technical thing, it's a bit disturbing where you're going to me, because why do you want a metaphysics in which you have a direction of time, causality, causation, influences, which are all the things that modern physics has taken away from our fundamental understanding of the world? It's exactly what we have shown is not there. So why do you want to bring back this sort of old physics, pre-Newtonian physics intuition to make sense of something that has getting rid of it? But let me go to the, sorry for this blah blah blah. Let me go to the let's suppose that C has to value. It rains today it rains, so today it doesn't rain, or one day it rains, one day it doesn't rain. So it's to rain, okay? And let's suppose that to rain, it's random, it's completely probabilistic, because determined by quantum transitions, whatever. And let's suppose that in my city where I am, the probability for tomorrow to rain is 1/2. And for not raining is also 1/2. So P of C equal rain is 1/2. P of C equal not rain is 1/2. Okay. And let's suppose that I am a very deterministic guy, that I'm very, very, very like Kant. If it rains, I go out with my umbrella. If it doesn't rain, I go out without my umbrella. Okay. So the probability that I bring out my umbrella if it rains is 1, and the probability that I bring out my umbrella if it doesn't rain is 0, and the probability if that I do not bring out my umbrella if it rain is 0, and finally, etc. Okay, so this allows me to compute the overall P E comma C probability, which is 0, 0, 1/2, 1/2, right? Because I just take your base rule and multiply by P of C, and I get both lights of the quality are the same, of course, and are equal P. And then, take any C, and you get your causality equation. The right-hand side, you have 1/2, And so on the left-hand side, you do not have 1/2, right? It's because in your interpretation, in other words, if I bring out my umbrella, it's a fact that it rains. So then you would say you interpret this as bringing out my umbrella causes rain. No, this has nothing to do with causation. To understand what we mean by causation, we have to go a completely different route, which has nothing to do with this use of probability. We have to go to the intervention notion, to the splitting the system in two parts, all the things that does in causation models. So this causality equation that you write down does make sense to me. I don't understand what you mean.
Well, it doesn't exactly because of this. Like if you consider these to be really probabilities from the beginning, if you think of this object to be all probabilities and these things.
Yeah, I think it's probabilistic here.
Yeah.
The probability of raining or not raining is 1/2.
Yeah,
the probability of me being reasonable is 1, me being unreasonable is 0. So it's the probabilities.
Yeah, but you are already considering the idea of probabilities as really being
frequencies. Yes.
Sorry.
Frequencies.
Frequencies.
Yes.
Yeah.
Yes.
And I mean, this is already dependent on the interpretation of probability to some extent. Like it doesn't. So I want them to be. I want this P not to be necessarily probabilities at the outset. I want them to be possibly this idea that they have like this direction of causation, which in your example, they are just like computing what is the correlation between two things to happen, and you renounce the idea that they might cause one another. So you are already, I think,
I don't understand what you mean caused by one another. I either understand there's a correlation,
yeah,
and you don't want that, or I understand in the interventionist sense, and you don't want that. And I don't understand what you mean then.
Well, no, they can be understood in the interventional sense if you want, but I don't understand. Well,
in the interventional sense, it's not true that PC given E is given P of C. It's just not true.
P of C given E.
Yeah, the probability that it rains, given that I've taken the umbrella out, is 1. The probability that rains by itself is 1/2. So that equation is false. And that doesn't contradict the interventionist things, which compare two different cases.
I don't understand why it's false. Like if you want
that it rains, P of C is it rains is 1/2.
Yeah.
And E, let's E be I have taken my umbrella.
I think it's a very reasonable assumption that if you want to call an event something that is so imagine this mode P. I think we're too conditioned on thinking that these are probability from the beginning. So you want them to be, maybe I've used the wrong. So the only part that tells this P's probabilities comes from here. This mode P here could, in principle, be a different arbitrary mathematical object that tells you that if you have a certain, that relates a certain event conditioned on what is going on before. So if it has a directionality that is imposed by this vertical line, is actually a directionality. If you don't want to use causation, you have to call it time. And I understand that you also don't want this, but like E and C, when I condition on something that happens afterwards, you don't want them to be able to have any influence on it. So you're really like you're really introducing like a directionality of what can influence each other. And clearly, if you have two events that you call cause and effect, you want to impose a directional distinction, a symmetry between what is a cause and what is an effect. And then
yeah,
you
we know how to do that. There are books written on that, right? All the causal modeling are ways to define that very precisely. But they don't imply your equation, which you call causality. Or if you want, what you mean by this equation, as you just said, the P in the second equation is not the same P in the previous equation. And therefore, bringing them together doesn't bring a contradiction because they mean two different things.
Well, this I don't see why they're two different things. Like, well, yeah, if you want, it brings a contradiction if you want them to be the same thing. Yes, that's what this example shows, I guess.
Right. So you agree that the probability of raining is 1/2. The right-hand side is 1/2, right? I
agreed with what you described with probabilities, yes.
Okay.
But and with probabilities not being
if it is the case, if it is the case that I broke out my umbrella, then the probability of raining, it's 1.
If you brought out your umbrella, then the probability of rain. I mean, I don't even know how to write this in this thing. Like, if I bring out my umbrella, so P of rain given you brought out your umbrella is 1.
Is 1.
Yeah, because your probabilities only are a measure of correlation. Every time it rains, you have the umbrella. Every time you have the umbrella, it rains. There is nothing that has a direction of causation in this event.
Right. So that,
yeah.
So that's not causality. That's right. So probability. So I don't understand what else.
So probabilities are the wrong. But why can you say these? Why can you say this thing? Is because you have like a way to reverse one in terms of the other. You can compare them because you have a Bayes rule. That's a property of the probabilities that you are able to build such an object. So without the Bayes rules, these two can exist independently. So yeah, these two objects are not necessarily this object. Once you call them probability, this holds, and then your argument goes through. And then we're not talking about propensities. So it's exactly your argument is correct. Is showing that what I call propensity cannot be probabilities exactly because of your counter argument. It's very similar to what Humphreys has said.
So what is? I don't understand now
what is a propensity.
Yeah, I just have no idea whatsoever. You're telling me that it's not the only reasonable thing that it could be. What else is it?
Is not something that measures correlations. So necessarily it has to agree with the probability, but it has to have like a.
But what is the difference between that and the angels that bring around the planets in the Keplerian orbits?
It's absolutely a metaphysical concept. Yeah. If you want
to add something which is not in the data, and the only
on the contrary, I don't want to add anything. I want to have like something that has that it's a minimal interpretation for me, this, because everything we've ever measured in science is uncertain and we are only able to give like intervals of confidence with certain measures of likelihood. What I want to tell you is that interpret the measure of likelihood as being the only structure existing. Everything else is a construct. The fact that we have like certainties and like differential equations with continuity and real numbers. Think of these as being like all constructions for simplifying the calculations. But since everything we had was always likelihood of something to happen or not, take these as being the fundamentals of our theories, and let's see how much can you push this. If you do that, they cannot be formally probabilities because otherwise they trivialize the
No,
problem.
no, this is a jump. Because likelihood is one thing. The power of something acting on something else and not reverse. It's nothing to do with likelihood and it's not in the data. That's something added.
I don't understand, Carlo, why is something like
Okay.
okay. Maybe we should discuss more more in detail. I would be very happy to. But
sorry.
In a different location.
Sorry, but I think all the point of Carlo is that rightly for defining causation, you cannot use just the simple probability here. I think the causality framework is very clear here. That you in the second line causality you can put P as probability, as propensity, I don't know, but you should put the conditioning is over an intervention on E. If I go out and I force people to take the umbrella, regardless of any other influence, then I can say that the rain is not changing. This is the intervention that define the asymmetry, the thermodynamic asymmetry that one has to have to define causality with an arrow. So here the condition is over it is called the do operation in causality framework. And it is an intervention on me. You assume that you can force a variable to be a certain value and see what other variables, how other variables change. Only in this way you can distinguish between a direct cause or a simple correlation. Only in this way. And Carlo is true that I think Carlo, the point of Carlo is that you should introduce the asymmetry, but the causality framework is very clear here. You can introduce the asymmetry by intervening on the variable E. If you intervene on the variable E and see that the probability of the event C is not changing, then you can say that there is no causal influence.
Yeah, thank you.
So, I think that you should just insert the intervention on E, do E. That is called just an operation.
I mean, again, this thing can be developed in many different ways and much more sophisticated examples. This was just, it's not even how Humphreys argue for this. It has like much more sophisticated ways of proposing this. I wanted to give you like an intuition of why this thing cannot be like directly linked. But of course you need maybe I should clarify. I take this as constructive criticism of clarifying what I mean causality that has never showed up before, but thank you. Yeah, I agree with you with the do-E works. Yeah. Claudio?
Yeah, so my main question is, as I mentioned for this ETH approach, I think, well, for all I can say at face value, it realizes everything you're asking for. So have you looked at this, or where does your considerations distinguish themselves?
The ETH interpretive approach, or
yeah, for this events, trees, histories approach.
Yeah. No, I'm actually. I mean, I know it exists, and I know more or less what it does, but I never tried to properly study to connect this. But now that you mention, well, I stumble upon it in a completely different context, not when I was working on this, and I actually never had the idea of connecting them. But now that you mention it, indeed, there is some similarities in the foundational motivations that I think that they can be really much related. Yeah, thank you, Claudia. I will have a look for sure. Now on the spot, sorry.
Yeah, as I said, like just at face value, it looks very much like a realization of Hussein. I mean, it's all like he worked it out. It's mathematically sharp, so all the definitions are there. It's relativistic, and yeah, so.
Yeah, I know that. Yeah, the good thing exactly that you have, like, I would like to see how their relativistic implementation goes with respect to
paper in the chat.
Oh, thank you very much.
Okay. Thanks.
I think Emanuele still has the raised hand from earlier.
Yeah, can I ask?
You want something to say? Yeah, of course.
Yeah. Okay, now I remove. No, I was just more basic. So if this trivial, just ignore me. But I cannot understand the passage. If imposing I mean a minimum volume in the phase space, okay, of the I mean the reality. Does this imply indeterminism, or indeterminism is a possibility? Because I don't see the necessity.
Okay. So the necessity is the following. So what is the volume in phase space is telling you that this is your actual state. This is a maximally complete information about the system. There is nothing in the universe more determined than this, right? Which gives you, I don't know, let's say that you have like it can be arbitrarily small, and it gives you an interval of, for instance, of position of a certain particle to be. Now this particle gets guided through certain equations of motion, so let's say Newton's equations. And it can have a certain potential such that the dynamics of this is chaotic. Actually,
okay, no, but if the dynamics is not chaotic, suppose the dynamics is not chaotic.
Well, first of all, dynamics not chaotic is a measure zero subset in all the dynamical systems. Like almost no system is non-chaotic. It's just that we physicists have been able to solve this, and we only do our tell to each other that everything is harmonic oscillators. Okay, but let's say it's not chaotic. If it's an integrable system, this volume, the volume doesn't work.
Doesn't work. Okay, but you are also assuming that the observables can be real. I mean, because in quantum mechanics you have an indetermination. When you observe the position, for instance, you can assume that okay, it is a direct delta in the position when after the measurement. If you have a minimum, if I can imagine a world in which I have a minimum discretization of, I mean, I have discretized space time. Okay. So I really cannot see something that is, I mean, more precise than discrete interval. So my question is, in this procedure, I don't see a measurement problem, because there is no collapse, because also the measurement is constrained by this minimum interval. So I don't see indeterminism why it is a necessity, apart from the dynamics.
No, I mean, these are two different questions. I think these are different questions. So one thing is that if you want to have like a, you know, this blob, which is my state, evolves in time, and then you have a certain trajectory, right? You want to say where is the position. Classical trajectories are thin lines that connect one point to another, like dimensionless thin lines. And in this case, if I have a blob, these can have multiple trajectories, right? This like unless it's really an integrable system where you have like a snake of at another time, like your word cube remains constant in size. It can usually remains constant in size. That's like a non-chaotic system. Like it goes around, but the volume remains the same. It doesn't get stretched. So this is one thing. The other thing is that when you want to measure it, maybe there is some process that reduces the volume, reduces the size. Like you can determine better something.
Yeah, I mean, the question is, you are assuming these dynamics in the measurement, in an hypothetical measurement, or not? Because I don't see the necessity. I can imagine a world in which all is discretized and there is no indetermination. I feel I can imagine. Maybe I'm missing something. just the question is if I have not a real, there are no real number, just I mean all is discretized. I can imagine a deterministic world, a deterministic physics. It is a necessity or it is just an assumption, your assumption? This is my question.
Okay. A discretized word. So these volumes are like there is nothing in between, really is discrete. Then
it's really discrete.
Yeah, I think there
is no real, there are no real number, no necessity of real number. Just
I think if it's discrete, you can have a deterministic dynamics, but you cannot. But there you really have to change things somehow, like more.
There is this all this work in cellular automata, right?
Yeah.
Like deterministic cellular automata. You can have deterministic, reversible, irreversible, and so on. But I think one of the assumptions that Flavio did not challenge whatsoever was this idea of having dynamical laws as ODEs.
Yeah.
As ordinary differential equations. In that case, if everything is discrete, then you won't be able to have a differential equation because differential equation uses the underlying continuity of space.
So you are assuming that the dynamics is I mean there is some continuity in the dynamics, but there is no continuity in the value of this, and this brings you to the necessity of indeterminism.
In the same way that quantum mechanics does it, no? Like you take the states and you evolve it with an ordinary differential equation, and this thing goes.
But indeed, in quantum mechanics there is. I mean, Brownian mechanics is completely deterministic. So you can say, oh, but Brownian mechanics assume a real number.
Yeah, in the same way, exactly. I see like a one-to-one comparison with these two things. If you discretize it, you cannot use anymore the standard mathematics for the dynamics. You have to find like some discrete objects like cellular.
Yeah, sure. Obviously it's different. Yeah, obviously it's different. But conceptually it can be.
I was looking for an interpretation in the sense that you leave like the mathematics of the dynamics the same, and you just interpret differently what is the state, the maximal informationally complete.
Okay.
Of course, there is other ways to do it. You can have like stochastic dynamics with real numbers. You can have non-continuous dynamics with or without real numbers. You can have all possible combinations. I'm just proposing one way to do an actual interpretation without changing the dynamics.
Thank you.
Thanks for the questions. Yeah, I hope it clarifies.
All right, is there anybody else who wants to ask a question, Flavio? I have a question. I don't know I hope it doesn't take too much time, but I'm curious about this story that your model also predicts that you have this model of indeterminism towards the past as well. I was curious about that. If you can say it like shortly, what you meant by that.
Yes. Well, the model is essentially trivial in the sense that you consider that you have a finite, so everything is based on finiteness. So if you have like a universe made on a finite amount of entities, particles, let's say, of systems, and that you have so all these all the evolutions are like in this propensity graph that I showed before. Then we consider like this idea of past, of present, defined by the graph that has propensities in the past and propensities in the future, and you quantify the amount of information that lies in the past and the amount of information that lies in the future. Since in the past you have finite entities that can encode only finite information each, then you have kind of a hard disk of the future, of the past, that at some point gets saturated. There is the system to compute how much you can put of information into this, and once it's saturated, you kind of erase the remote past, so it's kind of scrolling down. However, since the information about the past is only collections of zeros and ones, because everything is actualized, And instead, the amount of information about the future is arbitrarily complex rational numbers, because each propensity is a rational number between 0 and 1. If you want like to write down in a computer, in a string, the amount of information that belongs to the past and the amount of information that you record about the future, under the assumption that there is more or less the same amount of events in the past and the same amount of events in the future, you have like that the future is open, the past is open, but you have that the amount of information to record the past requires, so you can record many more events about the past than about the future, because the propensities are like only zeros and ones, and the other ones is like any possible number. I don't know if I give you a very, it was really in a nutshell, but that's it.
No, I think you
compute the information about the propensities of the past and the future under some assumptions. I call it a toy model because assumptions are kind of well, not very physically justified to say that there is as many events in the future than in the past. But if you consider some kind of homogeneity of events per time slice, then you can claim something like that.
Okay, that's interesting. There's one more question from Ale, Alessandro.
Maybe just a question for clarification on the same point of Andrea. Can we say that beyond, I mean, you describe an hard drive, which is not a finite information, only is a fixed information, where information can be finite and growing.
And unbound,
so my understanding of this randomness of the past is more on the sense that starting from the lattice that we're discussing with Emanuele, basically you have a certain information at the present, and when you look at the past and you try to compute the things that happens in the past, your error grows as the distance from the present grows. So you arrive at a point in which the noise, the growth of the error in the resolution of where the things were beyond a certain amount of delta t in the past is so much that basically you go to a fully random situation. So it's a matter of, in a discrete dynamics, the growth of the error about the knowledge of the finite volume that you have in the past can grow as well, given the fact that mathematically you lose information the more the delta t that you are using grows, basically. And this is true also in terms of information about the past. Could be this, I mean, understanding of the, or about a kind of irreproducibility of the past, rather than an actual being actual or not, is the fact that you cannot say, because the error on your estimation grows so much that the noise floor basically makes everything random.
I mean, yes, obviously, yes. I mean, this can always be the case. Like you can, since like what it was bothering Carlo also is that these things are unobservable in the sense that there is a very beautiful paper by Patrick Supps that he says that the transcendent character of indeterminism. Like you can always complete and incomplete, or like and take things away from fully deterministic, or complete things trivially also, that you can like, so there is no way that you can actually establish whether this scrambling of the past or the future is due to an error that builds up. Or I'm just giving you like proof of principles, alternative views, and telling you that these can be, for me, naturally interpreted in this way. Since we only observe this kind of uncertainties, why don't you take them to be like the real thing, and we try to see how much, because in the end is what quantum mechanics has led us to, and maybe it was not something. So if you have a take-home message from my talk, is that what quantum mechanics led us away from the comfort of classical physics perhaps was not necessarily there in the first place, and you could have already questioned this at much earlier stages, even from what we knew. So it was like a very nice idealizations, and perhaps was like
And of course, I mean, what Emanuele was saying is correct, that like if you don't have chaotic systems, then this is kind of is pointless, because like you start with 1 centimeter uncertainty, and in a year it's still 1 centimeter uncertainty. It doesn't really matter to interpret this indeterministically or not. But what I want to point out is that in physics, in the real world, there is very little systems that can be approximated by integrable systems. Not even the three-body system, not even the double pendulum. Like a very simple, allegedly simple systems have behaviors in which the uncertainty grows very fast and very abruptly. And I'm just proposing that maybe we should take this seriously and not like consider that everything is a harmonic oscillator that we can solve. And there is exceptional cases. The exceptional case is the integrable system that are very rare in nature, and maybe we should not take these as the norm and the uncertainty as the strangeness. I see I triggered more comments.
Yeah, Flavio, it's up to you. Like normally the question session ends when the speaker dies, so it's up to you if you have the energy to keep going. But obviously, this is interesting.
Maybe just a very short thought that comes to my mind. Perhaps a subtlety that I very much like about this classical point of view that you make about deterministic evolution, but measurements in kind of finite boxes. And the subtlety is the following. I think one can now view two different scenarios about indeterminism at the classical level. So one is like at, let's say, any fundamental time step, you choose some fundamental time step and you say, whenever there is a step, you make a random choice. And quantum mechanics is not like that. There are quantum events, but nothing really tells us when a measurement happens. No, there is nothing that, it's not like every Planck unit or every Planck time there's a quantum jump. We don't know when a quantum jump happens, but given quantum jumps happening, we can give probabilities for things to occur. And the same can be now, and in a way, this classical model can have the same features. So you can have a measurement problem in very much the same way.
Absolutely.
So I think this is really just a comment more than a question, but this is something that can be realized already conceptually at this classical level without ever having. So do I understand this correctly?
Absolutely. Thank you, Volker. Yeah, it's exactly what I wanted to say. Yeah, but you don't need to change like the dynamics, as you said, like that you have like a stochastic evolution of jumps, but you really have this model that you don't know when and why at certain point and it happens, but what we actually see is single events. Right. And if you have like different possibilities, then you have to explain, well, you ought to explain why and what is, you can refuse this by being many words, or you can find explanations of why this happens. Yeah, I fully agree with your summary.
Okay, cool. Thanks.
Last question from Carlo, I guess.
I wonder if you agree with this. I agree with your pointing out the similarities and stressing and the fact that sort of system that we know how to integrate are exceptional. But there's still, and this is what I want to know whether you agree with it, there's still a huge difference between classical and quantum systems as theories, because in quantum mechanics, generically, there are isolated systems where whatever we know about the system at some time, then in a finite time, there's just a full amount of information that we do not know. it's not exactly the same in classical systems. To the extent which classical mechanics is right, classical mechanics is telling us that if you want to know the state of the system, if you want to know what we can measure about the system in a finite time with a certain precision, we can always make a measurement at an earlier time with a precision such that we can get the required correct predictions within the given precision, which is not true in quantum mechanics, neither in the so-called indeterministic interpretation nor in the deterministic interpretations, because also in the Bohmians are not able to predict what's going to come out from a Stern-Gerlach any more than a Copenhagen, for different reasons, but it's a different metaphysical
For different reasons, yeah.
So empirically, the difference is still very large between quantum mechanics and classical mechanics, right? So in quantum mechanics, there's some irreducible finiteness in information gaining or information losing, while in classical mechanics, you can make it as arbitrarily small as you want to the extent classical theory is right. So there is this difference. It remains. Would you agree with that?
Yeah, I do. I do with this. Yeah. But still, like the practical, most of the chaotic systems, you have like practical behaviors that like, yeah, in terms of like a matter of principle of finite amount, I agree with you. Yes.
Nice. And on that note, I guess let's thank again Flavio. Thank you for the stimulating talk and discussions.
Thank you all for the very nice discussions, and it was very useful for me as well. Thanks so much.
All right.
See you next time.
Bye-bye. Yes. Bye-bye.